Okay, let's dive into something you might not often think about living in your closet, but is absolutely critical for people on the front lines. The highly specialized fabrics in protective clothing, like firefighter gear or industrial workwear. We're talking about the challenge of recycling this stuff.
And it's a challenge that's becoming, well, unavoidable. Look at the sheer scale of the global textile industry. 124 million tons of fiber consumed just last year.
Wow.
Yeah, and that's predicted to jump to maybe 160 million tons by 2030. And along with that, growth comes waste. A staggering 20 to 25% of fiber is wasted before products even hit the shelves.
20 to 25%, just gone.
Just gone. The industry as a whole ranks second in pollution globally, right after oil. It's huge.
That puts the scale in perspective. So within that massive waste stream, why zero in on these specialized protective fabrics?
Well, because their use is increasing dramatically, the market for flame-resistant, or FR, fabrics hit nearly $5 billion last year and is expected to reach almost $7 billion by 2030. And the materials used, particularly inherently FR fibers like aramids, pose a unique environmental problem. They're built tough, often petroleum-based, meaning they just don't break down quickly in landfills.
And you mentioned inherently FR. Does that make disposal even harder?
Absolutely. Unlike some fabrics treated with fire retardants, these fibers are inherently flame-resistant because of their chemical structure, which often contains benzene rings.
Right.
And that structure is a problem for incineration. Burning releases toxic gases. So you have this growing category of essential high-performance textile waste that you can't easily landfill or burn. It's a significant environmental and, well, economic headache, too.
So for this deep dive, our mission is to figure out if there's a better way, specifically through recycling.
Exactly. We're going to explore the potential of mechanical recycling for these specialized FR textiles. We'll dig into how it actually works, uncover the significant technical hurdles that make it so difficult, and based on a comprehensive review of the research, sort of see what the path forward looks like.
All right, let's start with this hidden problem. You said these petroleum-based FR fibers, like aramids, don't biodegrade. What does that mean for landfilling beyond just taking up space?
It means they are incredibly persistent. They sit in landfills for, well, essentially forever from a human perspective.
Forever.
Pretty much. And as we discussed, incineration isn't a safe option due to toxic emissions. This leaves us with a mounting volume of tough synthetic waste that requires active management to avoid environmental harm.
Which makes recycling feel less like an optional nice-to-have and more like a critical necessity?
Precisely. Choosing recycling over landfilling or incineration offers concrete benefits. You significantly reduce synthetic fiber waste, conserve valuable non-renewable resources by giving existing materials a new life, and cut down on the high energy consumption and greenhouse gas emissions associated with producing virgin fibers from scratch.
And there are numbers to demonstrate that impact, right? I think I saw that in the review.
Yes. Yeah, the review highlighted a life cycle assessment. It found that a garment made with a yarn containing just 15% recycled meta-aramid fibers showed a 10% reduction in carbon footprint and a 14% reduction in resource extraction impact compared to an identical fabric made from 100% virgin meta-aramid.
So even just 15% makes a difference.
Think about that. Even a relatively small amount of recycled content makes a measurable positive difference. That's the potential power of getting this right.
That really underscores why this matters. Before we get into how you recycle them, what are the specific materials we're talking about? What gives this gear its protective power?
Okay, so the workhorses in high-performance protective clothing are the inherently FR fibers. The main players are the aramids. You've got meta-aramid and para-aramid, along with polybenzimidazole, known as PBI, and polybenzoxazole, or PBO.
These are the fibers literally protecting lives and demanding jobs.
Absolutely critical for protecting people in civil and military sectors. Firefighters, industrial workers facing hazards like electric arc flash or hydrocarbon fires, miners, the armed forces, you name it.
And aramids are particularly common, right? What makes them so effective against flame and heat?
What's fascinating here is their unique molecular structure. They're synthetic, highly crystalline, and built with these tough aromatic rings in their polymer chains.
Okay.
This structure is inherently stable under heat, preventing them from melting or dripping when exposed to flame, which is a critical safety feature. They also offer excellent mechanical strength and resistance to abrasion.
So meta-aramid and para-aramid aren't exactly the same. They sound similar.
No, they have different arrangements of those aromatic rings, which changes their properties. Para-aramid has a very linear, stiff structure, giving it exceptionally high mechanical strength. Think bulletproof vests or cut-resistant gloves.
Right, like Kevlar.
Exactly. That's a brand name for para-aramid. It can withstand temperatures above 400 degrees C before starting to decompose. But it has a weakness: sensitivity to moisture, especially acids and UV light.
Okay. And meta-aramid.
Meta-aramid has a slightly less rigid structure, making it semi-crystalline. It's got good thermal properties, starting degradation around 375 degrees C, and is widely used in industrial workwear, particularly in oil and gas. Its downsides are lower weatherability and poor dyeability. It's tricky to color.
And PBI and PBO push the temperature resistance even further.
Exactly. PBI has a very high melting point, well above 400 degrees C, and strong thermal stability. PBO is even more extreme, with a thermal decomposition starting way up at 650 degrees C and a very high limiting oxygen index, or LOI, of 68%.
Okay, LOI, what does that number tell us? I always see that spec.
Right. LOI is the minimum percentage of oxygen required in the atmosphere for material to actually sustain combustion, to keep burning. Normal air has about 21% oxygen. An LOI of 68% means you'd need more than 3 times the normal oxygen concentration for PBO to burn. That's incredibly flame resistant.
Got it. So it makes total sense these high-performance fabrics are often blends combining the strengths of different fibers to get the best of all worlds.
Precisely. And an important point for recycling: current performance standards for protective clothing, like NFPA 1971 for firefighter gear, they don't prohibit using recycled fibers if the final fabric meets all the required tests for flame resistance, strength, durability, and so on.
Okay, so the rules allow it.
Yeah, the challenge isn't the standard itself, but making a recycled fabric that can actually pass those really tough tests.
Which brings us to the recycling process. How is textile recycling generally approached? And why is mechanical recycling the focus here?
Broadly, you have 2 main paths: mechanical recycling, which is physically shredding or cutting the fabric back into fibers, and chemical recycling, which breaks the material down to its basic building blocks or extracts the polymer using chemicals.
And each has trade-offs.
Yeah,
Sounds like it.
Yes. Mechanical recycling is simpler and less energy intensive generally, but the physical process inevitably reduces fiber length and can damage the fibers, making them weaker. Chemical recycling can potentially recover purer materials, which sounds great, but it's complex, often requires separating blended fibers first, which is hard, and currently represents only about 1% of commercial closed-loop textile recycling. It's just not there yet at scale.
So why is mechanical the primary focus for these tough aramid fibers?
This is where the practical reality comes in. Mechanical recycling is currently the most mature, scalable, environmentally friendly, and importantly, cost-effective option available for processing aramid-based textiles. At this moment, it's really the only viable industry-scale method for recycling aramids.
Okay, the only game in town for now. But before you can even shred them, you need to collect the used gear, and I imagine that's a hurdle in itself.
It absolutely is. Collection rates for post-consumer textiles vary massively. The review noted figures from, I think it was 2013, 2015, ranging from only 11% in Italy to 75% in Germany.
Big difference.
Huge. In the U.S. in 2017, just 15% of annual textile waste was diverted. So getting a consistent, sufficient supply of used FR garments is a major upstream challenge.
Let's say you clear that first hurdle and get the used gear. How does mechanical recycling actually work for something as tough as FR garments? The review uses the example of a company called General Recycled.
Yeah, their process offers a pretty clear roadmap. It starts with collecting used garments and scraps, and ideally, they should be cleaned first.
I can see why cleaning would be crucial for protective gear, especially firefighter stuff.
Definitely. After collection, the materials are sorted by fiber content and color. Then comes a labor-intensive step: manual removal of anything that isn't fabric. Zippers, buttons, reflective tape, tags.
That's not automated. Seems like it would be slow.
Often not, especially for small batches or complex garments with lots of bits and pieces. Then, the sorted strip fabric needs to be cut down to size before shredding. And for tough aramid fabrics, this often has to be done by hand because they are so cut-resistant.
Wow, more difficult manual labor.
Exactly. After cutting, the material goes through shredding machinery to be broken down into individual fibers. These recycled fibers are then blended with virgin fibers. The type and amount depend on the desired properties of the final fabric.
Okay, so you mix them.
Yep. That blend is spun into yarns, then knitted or woven into new fabric.
And then dyed. Does that happen?
Typically, yes, through piece dyeing of the finished fabric. The final step is manufacturing new FR garments from this fabric containing recycled content. And the significant achievement here is that companies like General Recycled are successfully producing FR-rated clothing using recycled aramid fibers, and its performance is comparable to market standards.
That's impressive that it's happening at an industrial scale, but I know from the outline, just because it's possible doesn't mean it's easy. What are the major technical roadblocks once the material is collected?
Yes. This is where the deep dive really gets interesting. There are several significant technical hurdles in making this process efficient and the final product effective and, importantly, safe.
You mentioned cleaning. What kinds of contaminants are we talking about, and why are they so hard to remove? This sounds serious.
This is a major one. Use protective gear, particularly firefighter turnout gear, can accumulate hazardous residual chemicals deep within the fibers from fire exposure. The review lists some concerning examples: polycyclic aromatic hydrocarbons, PAHs, various organophosphate and brominated flame retardants, OPFRs, BFRs, polybrominated diphenyl ethers, PBDEs, and even metals.
So these aren't just surface dirt, they get embedded.
No, they can become embedded deep inside, and critically, they can be retained through the mechanical recycling process. This poses a health risk to the workers handling the material during recycling, and crucially, means these chemicals could end up in the new garments made from recycled fibers.
That's a huge safety concern. You don't want firefighters wearing gear contaminated from previous fires. What have studies found about trying to remove these chemicals?
Researchers have looked at various washing techniques. Methods like dry brushing, air blowing, wet scrubbing, standard lab washing machines, and even liquid CO2 technology were compared.
Liquid CO2. Interesting.
Yeah, it's quite effective. The liquid CO2 method in front-loading washing machines actually showed the best efficiency for removing contaminants compared to the other methods tested.
But the key question is it enough? Does it get everything out?
Not yet. And this raises an important point from the review. No currently established method consistently brings contaminant levels down to a clearly defined, acceptable level.
And we don't even know what that level should be.
Exactly. Defining that acceptable level for recycled protective gear is itself a critical research need. This is a fundamental challenge that requires much more investigation.
Okay. Beyond contaminants, are the materials themselves difficult to process through the machinery? They sound tough.
They absolutely are. Those strong aramids in the finishes they often have cause problems. For example, PTFE coatings, which provide water repellency, think Teflon-like finishes. They can gum up the rollers and shredding equipment, making the process really inefficient.
So they clog the machines.
Basically, yeah. Unless the coating can be effectively removed beforehand, fabrics with PTFE might need to be separated out before shredding, adding another sorting step.
And the shredding itself is rough on the fibers. You mentioned that earlier.
Extremely. It's a harsh mechanical process that significantly reduces the fiber length and can damage the fiber strength. Recycled aramid fibers are typically much shorter, averaging around, say, 26 millimeters compared to about 51 millimeters for virgin fibers.
Almost half the length.
Yeah. Plus, maybe 2–3% of the material just turns into unusable dust during shredding. It's lost material.
So you end up with shorter, potentially weaker fibers. How do you build that back up to meet the strength requirements for performance gear? That seems critical.
That's a central part of the engineering challenge, balancing performance and cost. The current strategy to meet strength standards is blending the shorter, recycled aramid fibers with virgin fibers.
Right, the mixing.
Exactly. Virgin aramid is expensive, often around $40 a kilogram. Blending reduces the overall material cost compared to 100% virgin material, which is good. But the more recycled fiber you want to include, which is the goal for environmental and cost reasons, the more you have to compensate for its reduced intrinsic strength.
It's a trade-off. What kind of virgin fibers are typically used in these blends?
The review gave some examples which are quite interesting. Virgin meta-aramid is sort of the benchmark. High strength, high LOI, but expensive. Monacrylic is cheaper, about half the price, with comparable LOI but much lower strength.
Okay.
Then there's nylon, much cheaper still, maybe $4 a kilo, and has higher strength than monacrylic, but a very low LOI of 21.5, meaning it's flammable.
Whoa, flammable. In FR gear.
Yeah, so you have to use it very carefully in the blend percentages. You also need small amounts, maybe 1–2% of anti-static fibers like carbon to prevent static buildup, which can be a hazard itself. It's a complex recipe to get right.
But we saw with the Ortex example that it is possible to make high-performance fabrics this way.
Yes, that example is very encouraging. Ortex created a knit fabric for arc-weighted clothing that's for electrical workers that incorporated 11% recycled aramid fibers within a blend. It was 35% total meta-aramid plus motacrylic, cotton, spandex, and antistatic.
Complex blend.
Very. And this fabric successfully passed stringent standards like ASTM F1506 and NFPA 70E, meeting minimums for bursting strength hitting 424 kPa, where only 345 kPa was required, and performance metrics like low char length, no melting, and a high arc rating of 10 calcium microsieverts.
So it worked.
It shows that strategic blending can indeed produce fabrics that meet tough safety requirements using recycled content. Bursting strength, by the way, measures how much pressure a fabric can take before it ruptures, obviously critical for durability in demanding situations.
So performance can be managed through smart blending, even with the fiber challenges. What about the visual aspect? You mentioned dyeing was tough, and these fibers often have color from their previous life.
All right, that leads to another hurdle. Dyeing. Aramid fibers are naturally difficult to dye because they are so crystalline and chemically inert. Getting color into them usually requires a lot of energy, water, and harsh chemicals. Or they are colored during the initial fiber production itself, called solution dyeing.
And recycled fibers come with their own color history, like little ghosts of the past.
Exactly. Recycled aramid fibers retain residual color. If you just threw a mix of colors together, the final fabric would look speckled, kind of muddy.
Not ideal for uniforms, usually.
Not usually, no. The industry approach to managing this right now is careful sorting and basically trying to use recycled fibers that primarily match the desired final color of the product. You also need to choose the virgin fibers in your blend strategically with color in mind.
And blending different fiber types creates another dyeing issue, you said, with temperatures.
It does. Different fibers require different dye bath temperatures to take up the color properly. Meta-aramid needs maybe 130 degrees C, wood acrylic around 90 degrees C, nylon only needs around 16 degrees C.
Big range.
Yeah. When you dye a blend, you often have to use a temperature that works for the most heat-resistant fiber present, but this could potentially damage or negatively impact other fibers in the blend if you get near their softening point. It just adds another layer of complexity to the manufacturing process.
So we've covered the current process and the significant technical roadblocks, contaminants, fiber degradation, blending challenges, dyeing complexities. What did the review identify as the most critical areas for future research and innovation to truly unlock the potential of FR recycling? Where do we need to focus?
Well, a major focus, maybe the biggest one right now, needs to be on the health risks associated with legacy chemicals in the gear.
And the big one here is PFAS, right? Everyone's talking about PFAS.
Absolutely critical. PFAS finishes per and polyfluoroalkyl substances are widely used to make protective clothing, water, and stain repellent.
Yeah.
They work really well for that. But we now know these forever chemicals pose serious health risks. Their stability, the very thing that makes them work, means they persist in the environment and bioaccumulate in living organisms. They're found in the blood of almost everyone tested.
And linked to high cancer rates in firefighters specifically.
Precisely. This makes PFAS removal from used gear incredibly urgent, not just for the environment, but for the safety of the recycling workers. And, crucially, the people who would wear the new garments made from this recycled material.
And regulations are coming.
Yes, upcoming regulations and bans, like California banning PFAS in firefighter PPE by July 2026, mean a massive amount of this gear will need to be disposed of safely soon. Developing effective ways to remove PFAS before recycling is essential if we want to produce new, PFAS-free protective clothing from recycled fibers.
Is there existing technology to do that effectively without ruining the fiber itself? It sounds really hard.
Knowledge in this area is still developing. It's really nascent research. Developing treatments that effectively strip PFAS from the fibers without degrading the essential properties of the aramids, their strength, their flame resistance, requires chemists and textile engineers working together closely.
Okay.
And we also need to figure out how to safely decontaminate the wastewater from these removal processes. You don't want to just wash the PFAS off and put it into the water system. It's a complex problem requiring significant R&D.
Definitely. Another area highlighted was the long-term performance of the recycled material itself. Protective gear gets put through the ringer, as they say.
It really does. The harsh conditions, heat, moisture, UV exposure, abrasion, cause the fibers to age over time. This can lead to performance loss, sometimes without visible signs, which is obviously a major safety concern for critical gear.
And different fibers age differently.
That's right. Meta-aramid and para-aramid age differently depending on the exposure. Para-aramid is more sensitive to water and UV. Meta-aramid less so, generally.
And we don't know how recycled fibers, which already have a history, will age compared to virgin fibers in a new garment.
Currently, there's very little information available on the long-term behavior and durability of FR fabrics made with recycled content. It's hypothesized that fibers that are already heavily aged might break down more during the harsh recycling process itself and not even make it into the final fabric in significant amounts.
So maybe the weakest links get filtered out.
Possibly, but this hasn't been conclusively proven, and the long-term performance of fabrics containing recycled fibers absolutely needs rigorous evaluation to ensure safety over the garment's whole lifespan.
It sounds like addressing these challenges, the contaminants, the aging, the processing, isn't something one group can do alone.
Not at all. This highlights the absolute necessity of interdisciplinary collaboration. Optimizing FR garment recycling is really complex. It requires combining deep expertise across textile science, polymer chemistry, dyeing chemistry, textile manufacturing, equipment engineering, and importantly, textile sustainability experts.
A whole team effort.
Absolutely. Academic researchers, industry partners, engineers, they must work together. Achieving economic viability also depends on building up the collection systems to get enough volume, that critical mass of used garments for recycling. And social acceptance of recycled content in protective gear is also an important factor to consider.
So pulling all this together, what's the big picture takeaway from this deep dive into recycling FR textiles?
Well, I think the potential is clear and significant. Mechanical recycling offers a feasible, sustainable solution for managing the growing waste stream of these essential FR textiles, diverting them from landfills and avoiding toxic incineration. This brings major environmental and potential financial benefits.
And it's not just theoretical, it's happening now, at least on some scale.
Yes, as the example of General Recycled shows, it is happening at an industry scale. But, and it's a big but, there are still significant hurdles to overcome, particularly around effectively removing contaminants, especially PFAS, managing fiber degradation during processing, optimizing dyeing for blends, and ensuring the long-term performance and safety of the recycled material.
So the path forward is paved with research and collaboration, needs more work.
Exactly. Further targeted research and strong industry partnerships are absolutely crucial. Only by working together can the process be optimized, challenges like comprehensive PFAS removal be solved, and the full environmental and economic potential of sustainable FR garment recycling be realized.
Thinking about giving a second life to a firefighter's jacket or an industrial worker's coveralls, life-saving gear that's been through intense conditions, the level of science and engineering involved just to make that happen is really quite remarkable.
It is.
It makes you consider the unexpected complexity beneath the surface of recycling even seemingly mundane items and what that might suggest about the potential for tackling other difficult materials we use every day.
It really pushes the boundaries of what we mean by the 4Rs: recover, recycle, reuse, reduce, applying them to these very high-performance technical textiles. It's cutting-edge stuff, really.